So our next session in the afternoon, we have loads of good stuff. Remember I said it's going to be the sort of the afternoon of ReSTIR and techniques that take that on. Our next session will have a speaker from NVIDIA, Tanki Jiang, who is a senior real-time rendering engineer at NVIDIA working on the Omniverse RTX renderer. And as a rendering engineer, his focus includes real-time path tracing light transport algorithms and systems, path tracing real-time neural graphics primitive, Gaussian, NeRF, ultra-realistic XR pipeline integrating path tracing and composition. Previously, Tanki was a rendering engineer intern at Epic Games, contributing to real-time ray tracing features for Unreal Engine. With a background in computer science, game development, and art design, he is passionate about pushing the boundaries of computer graphics and shaping the future. So let's welcome him.
Thank you, Natasha. And there has been a lot of great talk. I hope everyone's ready for some math. Welcome to continue the advancing real-time rendering games. I'm Tianyi Zhang. Usually go by the name Tanki. So before I start my presentation, I would like to invite everyone to think about what we have done with the previous talks. We always bounce off the rays. But in this talk, we're going to try to eventually have those rays enter the geometries. So Eugene is not here, but I'm very excited to present our collaboration work. We both worked on the Omniverse RTX renderer. This talk will cover how we achieve realistic SSS in real time by combining path trace, light transport with diffusion profiles. We'll see how our hybrid method deliver a very high quality SSS fast enough for current generation pipelines. So let's dive in. Let me start by showing everyone what we can achieve. So this stone lion statue is rendered with our technique using only a uniform transmission color and scattering distance. There's no any other texture mapping at all. All the rich detail you see come from physically based geometry intersection with the lights. What particularly exciting is what our result is closer to the ground truth offline path tracing than the state-of-the-art diffusion profile approaches. Here's another example with these marble chess pieces, showing similar improvements in realism. Moving to a different material, these candles have cylinder lights at the top of representing flames, causing light to bleed through and create those characteristic glow that you will expect from real wax. And here we have some candy that combine subsurface scattering with rough transmission for a semi-translucent material. Now, since we're talking about subsurface scattering, we must show the humans. This shot is rendered in real time with our approach. Pay closer attention to the ear, nose, and eyelids as I switch to the next slide for the ground truth. Sorry, not ground truth. Here's the same thing without our method. Now, note you can see all those subtle translucent effects completely disappear with only the diffusion profile approach. Let me flip back to our result, and now let's compare this against the offline path tracing ground truth. While there are some detail differences, our skin rendering captures significantly more detail with much closer ground truth matching. Before we dive into the technical detail, I want to highlight again one more thing about the material richness. This is how the candy looked like without any transmission, only subsurface scattering. And this shows only transmission. Think about some sort of rough glasses and no subsurface scattering. And by combining both BSDF together, those effects give us those really delicious looking candies we saw earlier. All right, now let's officially begin with the fundamental bit behind the subsurface scattering. There's a lot of S in this talk, so we'll see. Subsurface scattering is some fundamentally volume light transport inside objects. Light penetrates the surface, travels through translucent material, scattered internally. Then it exits at different points. This internal journey created the soft appearance and color bleeding we saw in material like skin, wax, and marble. I was in Italy recently and seeing those all beautiful Roman statues full of SSS. So here we are. You can see when light hits the surface, a portion of the light reflects into the marble. Inside, it might scatter off the mineral particles many times to lose some energy due to absorption. Eventually, some of that light finds its way back out of the surface at another point. The result is that the statue's shadow and shading are softened by this internal blur of light, and you can also see light bleed through. Sometimes it's hard to differentiate the SSS from the GI. But in this case, I did stand there for like a good 10 minutes, just studying the light, make sure everything is SS before I took the shot. So I can tell you guys, all the part I circled out, they are actually SSS. In comparison, those little glow on the leg are actually from the GI. More formally, SSS refer to the light transport within the solid object that behave as bounded volumes. We assume homogeneous material properties throughout the interior with the geometry acting as boundaries. When ray hits the surface, they can either reflect via the reflection BSDF, showing pink, or enter via the transmission BSDF, showing blue. Once inside, light undergoes volume transport just like participating media. So effectively, SSS is the volume scattering that happens after surface transmission, where light can scatter multiple times internally. High-quality offline renderer handle this through random walks. For each entering ray, they stochastically sample scattering distance and directions, repeating this process until the photon either gets absorbed or exits. These random walks require many samples to converge, but they serve as our accuracy reference. We'll continue comparing our hybrid method against these random walk simulations to make sure we capture the important effects. Let me show you two examples of what random walk could produce. On the left, we have a very small rectangular light placed almost against the surface. You can see how light bleeds through the scatter before exiting. In the middle, a large light from above creates those signature bright edges, making the cube appear almost like a blob of smoke. Compare this to the solid code on the right, which is under the identical lighting. Now that we know that SS entails physically, let's talk about how we model SSS materials. For production SSS material, we need specific methods that are both physically based and R-friendly. When we think about material, it's common that we're thinking about subsurface property of the appearance. To define SSS properly, we need to explicitly define its volume behavior, how things behave within the mesh. We assume homogeneous volumes with properties determined at ray entry. This is common even for offline rendering. While not perfectly accurate for complex material like human flesh with its varying tissues, it's a reasonable approximation that provides performance benefits. Renderers ultimately need absorption coefficients, scattering coefficients, and entropy. Unlike actual participating media, SSS does not have emission. We expect the emission is pre-integrated and expressed as part of the surface properties as what you would expect in a normal renderer. However, these parameters aren't intuitive for artists. We must provide a high-level color mapping parameter instead. Color reflects the general appearance, while smaller mean free path values create denser materials that eventually approach reflection-only behavior. Those parameters can be texture mapping too, to offer maximum flexibility for artists. So here are some examples. You can see color reflects the general appearance of the material, while with smaller MFP, the material behaves more and more dense, which eventually becomes almost like a reflection-only material. So here is how we solve this. We compute volume coefficients sigma t and sigma s by first calculating an intermediate value s from the color parameters, combining this with the entropy g to get a single scattering albedo, then divided by the mean free path. Now, before I describe our hybrid approach, we need to really understand the diffusion profile first, the technique that's been widely used for real-time SSS approximation. As we saw, full volume rendering is complex and slow. This is where the BSS RDF concept comes in. It generalizes the BRDF for light entering at one surface point and exiting at another. Diffusion profiles are essentially pre-computed BSS RDF functions that show how light spreads across the surface after entering the material. The widely used profile in game rendering is based on Burley 2015's work. I want to lay more emphasis on how the profile is built. Borel diffusion profile is built based on the Monte Carlo simulation and curve fitting under such so-called searchlight configuration. Imagine an idealized scenario, a semi-infinite flat surface of a homogeneous material. Semi-infinite means the surface extends infinitely in the xy directions and is infinitely thick and deep into the object. This ensures we don't lose energy because light exiting through the back of the object. Then we shoot a light beam perpendicular to the surface. In this picture, you actually see there are 4 beams, which just represent 4 independent samples. The Monte Carlo simulation measures outgoing light versus the distance from the entry point, producing a diffuse reflectance profile, R, for a given material properties. Since the surface is infinite and flat, this outgoing distribution is this outgoing distribution has a circular symmetry around the entry point, which gives us a clean 1D radial profile function. This is powerful because diffusion simplifies 3D light transport into a 2D surface integration. Instead of simulating volume scattering, we simply evaluate pre-computed profile over distance, directly returning the effect of multiple scattering. When we compare against the ground truth, we see the diffusion quality degrades significantly with increasing scattering scale, even for simple materials and geometry. This is because the diffusion works best when surfaces are locally flat and large compared to the scattering distance. But as you can see in these examples where scale increases, screen space scale increases, the screen space samples, like I said, LLS, which are shown in blue, spread out and accuracy start to decrease. Eventually, samples scatter so far that they violate our assumptions that we mentioned earlier and create biases. So you get the same phenomenon when you actually can get the same phenomenon by just have the same material and scale down the model with the same identical materials. Let's walk through this video. Like before, we have an SS cube with a small rectangular light placed right against its surface. At the start, I leave the dome light on so you can get a better sense of the scene layout. You'll see once I switch the real-time view with the diffusion profile, pay attention to the bright spot, the size, the brightness. It matches the ground truth pretty well. Then I disable the dome light to isolate the light beam effect. They match very well. As I shrink the cube down into a slab, you will notice the light begins to bleed through the back. I flip between real-time and the ground truth. Notice the real-time has a bigger spot than the ground truth. At that point, the diffusion profile breaks down. It no longer matches the ground truth because now a lot of light is escaping out of the far side. The assumption of semi-infinite thickness no longer holds. And once I thicken the slab, it matches better again. Originally, the cube was thick enough that even though it wasn't infinite, it behaved close enough. But once the shape thins out, the same dense materials start acting sparse. Diffusion keeps trying to scatter light as if it were still deep and ends up overshooting the effect. This highlights a core limitation. Geometry isn't explicitly handled by diffusion. Things like thickness, concavities, or sharp curvature aren't really part of the model, and it has no awareness of the actual shape. So understanding those diffuse limitations, let me now present our new approach, which is based on our observation we've made about both strengths and weakness of the current method. During our development, we noticed something very important about subsurface scattering in typical assets. Looking at those renders with different bounce counts going from 0 to 1, going to 0 to 1 bounce makes a really huge visual difference, capturing most of those characters. But adding more bounces often yields diminishing return. It always just kind of soften and saturate the look a little bit more. Our approach accurately captures zero and single scattering through ray tracing, giving us the detail and the directionality of full random walk for those very critical first events. For multiple scattering, we use diffusion approximation to add the soft, smooth lighting those higher bounces will produce. Tracing limited bounces is much cheaper than unknown bounces, while diffusion evaluation remains very fast. So let me focus on the accurate single scattering part of our solution. Applying this PDF approach to volume rendering creates a separate integrals, one purely for scattering contribution and one for unscattered transmission. And as I mentioned before, emission is modeled through the surface property, which means we can ignore the emission term within the volume transport. We label these as the scattering term, which handles exactly one volume scattering event, and the boundary term, which covers zero scattering where light just passes through. This separation clarifies our computation target and dramatically simplified the original equation. The boundary term is actually really nice. It's analytical, so we only need Monte Carlo to estimate that the other integral, which is the scattering term. The key challenge becomes sampling the scattering distance t with the proper distribution. For varying sigma t, this sampling could be quite complex. But fortunately, since SSS assumes homogeneous volume with constant sigma t transmittance, TT followed an exponential distribution according to Beer-Lambert law. Using uniform random number between 0 and 1, we can normalize TT to create a sampling PDF. The inversion method gives us a simple logarithmic form. Now, TT has this exponential distribution, but since T can theoretically reach infinity, TT doesn't reach 0 at the volume boundary. This means our random sampling might fall outside the volume entirely, forcing us to discard samples. We can improve this by sampling the scatter distance while knowing that ray will exit at distance d. Constraining t between 0 and d reduces both variance and waste by renormalizing the PDF appropriately. There are two key implementation details worth mentioning. First, we need the transmission BSDF weights as surface entry and exit. This is often simplified by assuming the diffuse transmission leads to SSS. Second, once we choose the scattering points, we need to sample new directions using the phase function. We use the standard HG phase function, which has an analytic sampling method. Here's how our algorithm works in practice. We handle rays that hit surface and decide to enter objects. The ray direction comes from the sampling and transmission BSDF. This could be pure refraction for smooth dielectric or diffuse transmission for rough translucent materials. Our algorithm isn't limited to any specific BSDF type. Next, we trace the ray through the interior until it hits the opposite surface at a distance d. This is just a standard racing intersection test continuing from the entry point. At the exit point, we treat the interaction like a normal surface hit. We sample the transmission BSDF to determine how the ray leaves the surface and perform line radiance sampling at the exit point. Now, for the single scattering component, we know that exit distance d, we sample a scattering distance t0, use fresh random numbers from our derived exponential distribution. Then we sample the phase function to get a new direction for scatter ray. After scattering, we cast another ray from the scatter point in this new direction to find where it exits the object. Our sampling method handles two cases based on the sampling distance t. First case, t1 is less than td1. That means the scatter point is inside the object. The photon scatters before reaching the far side. This ray will continue scattering within the volume, representing the multiple scattering energy, which we ignore in this algorithm. Second case, T1 is greater than or equal to D1, meaning that sampled scatter distance is beyond the exit boundary. Essentially, no scattering occurs before the photon leaves. In this second case, we perform exit transmission BSDF sampling and light sampling for the scatter rate at exit point, gathering the single scattering energy contribution. Let's check out the result term. Because we got the T0 and T1 both through sampling, you can see we need to apply both PDF. Then the exponential term, which is the TT, then finally the radiance with BSDF weight F. We use the basic sampling distribution here because we can perform an adjusted routing instead. Instead of casting ray first, we can sample the distance first, which will help to determine optimal Tmax for the recasting. Unfortunately, since T1 is sampled, the variance could increase. Alternatively, if reducing variance is more important, we can instead cast a ray with infinite as the Tmax to solve D1 first. then we can write our estimator without without T1. So if we do everything correctly, here's what you will get. The image on the left side is rendered without any cache, so it almost looks identical to the ground truth. On the other hand, you might see some subtle difference here and there compared to the right picture. Either way, the point is the single scattering should match very close to the offline path trace ground truth. All right, we've handled the first bounce with full fidelity. Now we need to add back the multiple scattering components, everything beyond the first scatter. This is where we bring the diffusion profile approach. Let's continue with the same line head example we saw. When we first tried adding diffusion profile to our single scatter results, something looked wrong. The image appeared oversaturated and too bright. The issue is that the Broglie diffusion profile inherently includes a single scattering contribution since it captures all order of scattering. So by adding our explicitly single scattering first bounce on top, we were effectively double counting the single scattering component. With energy conservation, we know that single scattering plus all high-order scattering should sum to the full profile. So if we want a multiple scattering only profile, we can construct a single scattering profile, then subtract it from the full diffusion profile. But the mathematical foundation is that the scattering events can be expanded as a Taylor series over a single scattering albedo. Each scattering event multiplied by an albedo term, so n scatters would correspond to albedo raised to the nth power. For this expansion, we need to consider diffusion profile as function of alpha rather than this radius. We start with this formulation from Broglie's original paper, make the necessary parameter substitutions. To make it easier to read, I highlight the variable with color. You can consider everything else are just some constant value in this context. The profile RR consists of a capitalized A and S. We would like to express both A and S in the form of alpha. So this boils down how to express capitalized A as a form of alpha. To complete this transformation, we run our own Monte Carlo simulation to find the relationship between surface albedo A and our alpha parameter. With the additional formula, we can represent S as the function of alpha. Plugging everything into Mathematica produces this clean analytical result. Now, with our single scattering diffusion profile in hand, we subtracted from the original full profile to get our multiple scattering profile. The results with this new diffusion profile show much better ground truth matching. And that concludes our algorithm description. Now let's talk about the performance. Our open source SDK implementation implements the whole algorithm within real-time path tracer. Means the frame is rendered through a path trace kernel, then we use a denoiser to denoise the final result. The SSS vertices cost 4 rays per pixel, where 2 rays are shadow rays. This thing has almost 14 million triangles, and for this exact shot, the main rendering kernel costs 2.38 milliseconds. I would like to explain the whole routine to give you a clean picture of the workload. So let's pretend this bunny is the lady we just saw for a second. We start from the camera and trace primary ray. Upon primary hit, we perform next event estimation with a shadow ray. Then we sample BSDF events. If we manage to sample the transmission event, SSS happens. Also note that the dot line arrows all represent the shadow rays, which are just rays marked as accept first hit and end search. The kernel then samples the radius for diffusion profile and casts a ray towards geometry to retrieve the geometry sample. From that point, it performs an explicit light sample to complete the diffusion profile sample. After that, it goes through the single scattering routine we discussed before, which caused 2 regular rays and 2 shadow rays. So more detail about this thing here. Although we terminate the path after SSS, the reflection GI can go up to 8 bounces. In this thing, this helped to render the hair. Thanks to the path tracing nature, the implementation could handle indirect SSS event with refraction. For example, part of the face is behind glasses, and also notice those eyes here. The corneas are separate glass geometry layers, and right behind we have the choroids, which are modeled with an SSS material. Unfortunately, we are still away from solving SSS. Although we are quite happy with the quality, we can still spot some major differences if we compare it against the random walk ground truth. Because how diffusion profile is built on very specific material configuration, the color mismatch could happen with different material layer model. For example, here I added a reflection lobe, which causes the irradiance cannot be trivially sampled, and the weight of diffuse transmission becomes incoming direction dependent. On the other hand, materials with medium range density relying on multiple scattering to have those very translucent appearance. The application of multiple scattering diffusion profile means we miss some of those energies. Notice in the picture, the left one and the right one all matches closely while the middle ones lack some of the color bleed. This brings us to fundamental point. Rendering essential for sampling essentially is a sampling problem. We need to sample light sources for correct irradiance and solve visibility terms, which require understanding of the underlying geometry. For SSS, this geometric understanding becomes even more critical. While our algorithm flattens multiple bounds random walks into a consistent process with determined costs, the overall quality really scales with the capability of sampling for both lighting and geometry. We have to answer many questions like, how do we sample area lights? How do we handle many lights? Do we have budget for the hardware ray tracing? If not, what about screen space ray tracing? The algorithm itself does not really specify how to do any of those. It can be implemented to reuse whatever the renderer have and get improved with the underlying sample quality. When assuming a diffuse transmission BSDF, irradiance is the integral of radiance over hemisphere, which is widely used for diffusion profile. For every sample of diffusion profile, we require one sample every irradiance from the target pixel. Then recall what's described in the single scattering algorithm. We need 2 irradiance samples per path trace single scattering sample. LTC provides direct formula of computing irradiance without accounting for a visibility term. Combining it with a ratio shadow estimator, it can be used as one approach to estimate irradiance. Sample-based lighting has become popular in the recent years to handle the many light sampling problem, in which case we compute noise irradiance samples. For every sample, we combine mechanism to select a specific light from the scene, then optionally sample a point from the area light primitives. This resulting in a PDF for such light sample. An engine does similar sample-based lighting could estimate irradiance by doing one sample in Monte Carlo integration. We will touch more on ReSTIR in the next slide, but for completeness, any further ways to improve the irradiance quality will be beneficial for the implementation. Before we discuss the specific of ReSTIR, let me quickly cover the basis. To sample an unknown distribution F, with important sampling, we can perform RIS. Given M samples through an approximate target function p hat, then select one sample Y and use Y to compute F, weighted by the RIS weight. ReSTIR extends the RIS process by streaming samples into fixed-size reservoir while reusing samples from spatial neighbors and previous frames. For subsurface scattering, the central challenge is determining optimal ray directions within the volume. 2 factors guided this decision: radiance strength and scattering distance. We adopt a target function based on the boundary turn, which is practically beneficial because it requires no extra computation when sampling from our reservoirs. Here's our process. Step 1 is the same. We have the same goal, specifically F represents the boundary turn and Y represents the sample direction. Step 2, first we generate one sample, which means M equal to 1, where X represents the refraction direction. Then we use the boundary turn F to be our P hat. Then we plug in M equal to 1, P hat equal to F. We get a very important formula. This is exactly what we want to solve, actually. Then finally, let's look at step 4 first. We notice that W is exactly what we need for the sample. This eliminates the process of using directing to reevaluate F. Let's go through the whole process all together. First, X, Y represent the refraction directions. After entering volume, we sample the boundary turn, but instead of using such sample directly, we feed it into the reservoir, which is in the step 2 here. We then read the reservoir weights as our sample weights, which is step 4. This works elegantly because the P hat equal to F, as shown in step 2, so everything cancels out perfectly. Without this approach, we will need to have an extra ray for step 3 so that we can evaluate the geometry distance d. This routine has a constant overhead for just one boundary turn sample, costing 1 extra ray per frame. For example, for this bunny, we launched a path, sample transmission BSDS once, cast the ray, compute boundary turns, feed the reservoir, then loop over 5 samples, repeating this process if the setting requests 5 transmission BSDF sample. Every transmission BSDF sample effectively counts as 1 temporal reuse, and we perform standard spatial reuse in screen space with simple calling. In this scene, we have an object illuminated by a rectangular light and a texture mapped dome light. The dome light actually illuminates the scene. The results speak for itself. Our specialized ReSTIR approach substantially reduces visual noise with only 1 sample and at 1 ray constant overhead. Finally, for radiance estimation, we can deploy a caching mechanism for performance or quality improvements. For instance, we implement a backface irradiance screen space cache to capture irradiance. Capture irradiance distribution on the backside of geometry. This is especially helpful when drawing multiple samples, though in practice, we only need 1 sample since the RSS can denoise the signal effectively. I have 2 bonus slides that explain some practical tricks. At the same time, make sure to check out our character rendering SDK for an open source reference implementation. I'm short on time, so I will just quickly mention what they do. First is there's a very simple trick to help you to bring back all the details from all the complicated texture mapping when you feed the source noisy result into the denoiser. The second is when you sample in the distance, the sigma t is an RGB value, but you only can use 1 value to actually sample the distance. So in this case, you will need to do sort of a random sample the RGB channel first, which will derive you a PDF, can be used for this kind of sort of hero tracking. Finally, I would like to thank all the colleagues and the industry friends that helped us along this journey, which made this presentation possible. Also, we are very grateful for the whole graphics community where we found abundance of information for the development. Finally, I want to express my gratitude towards our amazing artists who made all those beautiful assets available for my presentation to take. This concludes my presentation. Thank you very much. Next question time.
So we have a couple questions. First one will be from David Corner. How does, I'm going to paraphrase it, you compute the radiance contribution from the light source at the exit point for perfectly specular materials? The PDF in that case is a delta function, so the contribution to the camera array is 0.
So if I understand correctly, is when the actual specular event is a delta event, you cannot really integrate over that function. We have a simple trick to climb the roughness, so at least it has a little bit roughness. And if it's an actual delta function, we actually have a special branch to, instead of sampling the BSDF, we just say, okay, this is the direction, go. And it also do the MIS weight with the BSDF sampling, so that part of the contribution can get weighted out. I hope that makes sense. Please reach out to me if it doesn't.
You can also expand upon it in Discord as well.
Yes,
for more details. Alexei Lisova asks, have you tried this SSS result on the artists? All right, with the artists. Were they more happy? I think you should still do what he says. Were they more happy? And clearly, they're freaking amazing. The content in this is outstanding. Were they more happy with this result comparing to a more vanilla SSS algorithm?
I think they're pretty happy because they made all those assets. But I'm not sure with different audience, that might be different. Our artists all come from a very offline focused background. So they are very happy when whatever they do in the Blender or other DDC tool, they render it offline and bring it to our renderer. And we also have a reference path tracer, and they look very similar quality. So they are very happy, and they can have very close quality to what they do as the look dev with the offline path tracer.
Super. We'll ask a couple more, and then we'll continue the questions that are coming in at Furious Space at Discord. I hope I pronounced this correctly. Zhanyu Zhu asks, are there plans to explore whole path reuse options?
Yes. This implementation for ReSTIR has a lot of consideration for performance because it's very simple and it's very cheap. But as some of you guys have seen, we implemented our sister team or our colleagues implemented some ReSTIR PT or similar more complicated ReSTIR technique in path space with our Zora demo with UE5. So definitely those can be one of the directions we consider to explore.
Okay, next question is from Michal Drobot. What is the practical range of material scattering, roughness, thickness that could work? In other words, thin paper and object behind, Japanese shoji doors.
Those work perfectly. Actually, one of the unit tests in our code base is just like a very thin slab of SSS material, and we slap a giant rectangular light, like an actual rectangular light, and it can give you kind of like the glow of the light shape, which is really cool.
Super. At this point, we're going to continue the answers on Discord because we've got to move to the next session, but let's thank the speaker for an awesome talk.
Thank you very much.
Thank you.